Thomas, and this is my heat transport video project. Whiskey stones. Why are they bad? Why are they so terrible at doing the job that they're made to do? So whiskey stones are these cubes of granite or soapstone. Mine, the ones I'm going to be using are soapstone that you put in whiskey below like 80 proof so that you can chill the drink but not dilute it. You put them in the freezer and it's supposed to chill the drink, but they don't work very good. They don't really work that good, like at all. Not as good as ice, not even close. So to find out why these stones don't chill liquid very well, I'm going to try to find the convection heat transfer coefficient H, which is the rate heat transfer between solid surface and a fluid per unit surface per unit temperature difference. My whiskey stones are made of soapstone, so I looked up some knowns on Google and found the density, the specific heat, and the thermal conductivity. So to do this, we need to first make some assumptions. I'm assuming that one side is adiabatic because one side is going to be resting on a surface. I'm assuming that the stone is a semi-infinite solid. I'm assuming the values I found on Google are right, that my thermostat is correct, and that my thermometer is accurate. I'm also assuming that frost or condensation buildup on the surface of the stone does not affect the convection. More about the semi-infinite solid assumption. The Fourier number has to be below 0.2, so I need to find a time scale that would work to make this assumption valid. So I found the volume and the surface area of the square. Surface area minus one side. The squares are about 2.2 millimeters in all directions. So found LC, found the alpha, and found an appropriate time scale to remain below 0.2 is 21.1198 seconds. So I'll be measuring the temperature change over the course of 20 seconds.
Hey, didn't see you there. Time for the experimentation part of the video. So these are the cubes, these little soapstone little guys. Put them in the freezer, they get cold. You put them in a glass and you click them around and feel sophisticated and not like stupid for buying them in the first place. So this is our adiabatic surface. It's an oven mitt. It's made to not conduct heat. So I think it's a pretty good adiabatic surface. This is our temperature gauge, laser. It's not super accurate, but it's the best thing I have for measuring surface temperatures. It measures in increments of 0.5, unfortunately. All right, let's get into it. Stop. Okay, where is it? Encrusted. Here's the sneaky little guys. Okay, let's see if I can get one. Yeah. Oh, okay. All right, got one. All right, gonna let it sit, let it settle down, let it kind of, it goes kind of wacky. Temperatures go kind of wacky when you first measure it, so let it sit for just a couple seconds, and then I'm going to shine it with a laser, count to 20. All right, looks like, it fluctuates a little bit, but I think it's safe to say that we went from 26 to 27.5. That seemed to be, besides the big fluctuations, that seemed to be the most stable ranges that it's at.
Okay, so now that we have some temperature values, we can do some math. Don't laugh at the handwriting on these slides. I dictated this to my 2-year-old little cousin, and if you laugh, he'll be upset. Don't laugh. So for case number 2, The flux is the same for all surfaces, and now we have our temperature at t equals 20 seconds, x equals 0, and our initial temperature. So this is our overall equation. And then at surface x equals 0, we can simplify this a good bit to get this right here. And then solving for flux for Q naught double prime, we get this. We plug in 27.5 for our temperature after 20 seconds, and then 26 Celsius for our initial temperature. Plug in the rest of the values, and then calculate it to get 1,820.267 watts per meter squared. So now that we have flux, we can just use Newton's law of cooling to find H. We plug in 27.5 for T for the surface temperature, and then 68 degrees Celsius for T infinity. We do the math and get a final answer of H equals 44.944 watts per meter squared Kelvin. We can just kind of mess around and go a little bit further to see how changing the surface area and volume affects this value. So these small squares don't really do a very good job of cooling down a liquid. Because the convection and the resistance to convection is dependent on surface area and volume, you want to minimize the surface area to volume ratio. So these small cubes don't do a very good job. If anything, you want a large cube. Even better than a cube would be a sphere. So don't buy this. If you buy anything, buy this. And don't even use this. Just use ice. Thanks for watching. I hope you enjoyed it.